Today we will be learning rotational kinematics. So we have learned motion in one dimension or two dimension. Anyway, the motion is linear, so we are interested in a project moving in straight in one dimension in x or y, and we have 5 kinematic equations. Now if we recall, we have 5 variables. We have 5 equations, but in each equation we only have 4 variables. So which means as long as you have 3 known variables, you can use one of the kinematic equation to solve the unknown variable. And this is basically the same for us for rotational motion. What we need is that we just need to understand what are the definitions of the kinetic variables for rotational motion. Now, please quickly go over the variables in linear motion. We have, for example, in constant acceleration motion, we have final velocity, initial velocity, acceleration time, and we have displacement. Those are the 5 variables we have. Please try to recall the definition and which of them are scalars, which of them are vectors. We want to understand rotational motion. We need to know what is definition of rigid object or rigid body, and we need to understand the kinematic equations for rotational motion. Now you see there are 2 different kinds of variable. For example, this one, which is the one we more used to. For this variable, you see the passenger the rider is always facing up, so you see the orientation of the seat never change. And then you have fixed, another kind, you have this basket always fixed. Now, which of these is rotational motion? Is this one rotational motion or this one rotation? We're interested in this chapter. Now the answer is that we're interested in rotational motion on the right. This one we are not interested in because it's hard to describe this use angle. Now if you look at what's happening to the right hand side, the motion of the right hand side, if you have a passenger here, this is nose. Its nose is doing a perfect circle around the rotation axis. And then the center of his body is also doing a perfect circle. The shoes of the rider is also doing a perfect circle. And this is rotation of a rigid body. What is a rigid body? Now, rigid body means 2 points, any 2 points of this rigid body, so the relative position of those any two points doesn't change. So in such a way, two points in the same rotational motion, they will rotate the same angle. So that's the definition of rigid body, and we're only interested in rotation of rigid body in this chapter. We don't interested in any object. Its shape is changing and it's rotating. We are not interested in that. Now, after we fixed the definition of rigid body, we need to, let's take this potato, rotating potato as an example. Now, if you recall, in linear motion, we need to define a coordinate system. Coordinates, and you need a positive x and a positive y. And for rotation, you also want positive and negative. Otherwise, different people will be confused. For example, you have this potato rotating. She saws it rotate counterclockwise, but he sees it's rotating clockwise. So what can we do about this? What we do is that you need to choose a rotation axis. For example, for this potato, if you choose this to be rotation axis, then rotating counterclockwise is positive. Rotating clockwise is negative. But first of all, you need to choose the direction of your rotation axis. Now we know this potato is rotating around this screw or rod, but you have to pick the direction of this barbecue screw such that this direction is positive, then this is positive for this rotation axis. Now of course you can choose, for example, this potato, you can also choose this direction to be your rotation axis. Now that's your choice, but after you choose the direction of your rotation axis, then see, this is negative now. This is positive because this is clockwise from this rotation axis. This is negative. No, this is counterclockwise for this rotation axis. And for rotational motion, we have to use readings as a unit for angles. And this is a geometric property. So if you have an arc on a circle, the length of this arc is related to the radius by this. So S equals theta times R, which of course gives you theta equals S over R. So which means if you use readings, you just multiply this angle with R, it will give you the length of the arc, which is this angle corresponding to. Now you have this potato initially here, and then you rotate the angle from here to here. And now the difference of those two angles, we call it angular displacement. So this angle is the initial angular position. This angle is the final angular position for this potato. And the difference of them is angular displacement. Just like displacement is final position subtract the initial position. Basically exactly the same. Now if you remember whether displacement is vector or scalar, you should recall that displacement is a vector and so does angular displacement. Now we all know vector is associated with the direction. Then what's the direction of angular displacement? And we're going to talk about more later, but anyway, angular displacement is in the direction of rotational axis. So in this case, you have x here, you have y here, then your z-axis actually is pointing out of this screen now. Right now, positive z is pointing out of the screen. And this potato is rotating around z, if you can see this. This potato is rotating around z. So now let's draw it this way, x, y, z, and if you are rotating in the xy plane, then your angular displacement is in the positive z direction. That's the direction of your angular displacement. Have x, y, and then your rotation axis is pointing to the positive z, and your angular displacement is in the direction of positive z. Now if you recall, velocity is displacement over time, and this is exactly the same for angular speed. Angular speed is angular displacement over time and give us angular speed. And if you take delta t to be very, very small, almost as small as 0, you got differential of angle position over time give you angular velocity. And angular velocity is a vector as well, because angular displacement is a vector. And angular velocity should follow the same direction as angular displacement. Now in this case, your angular displacement is on a positive z pointing out of this screen, so your angular velocity is also positive z pointing out of this screen. Yeah, and there is a right-hand rule, so you just put your 4 fingers along the direction of rotation. Your thumb will give you the direction of angular velocity. This is right-hand rule. And also we have another quantity called angular acceleration. If you recall, acceleration is change of velocity over time. You have angular acceleration is change of angular velocity over time. Now of course you take delta t to be almost 0. Angular acceleration is differential of angular velocity over time. And angular acceleration describe how you rotate faster or you are kind of rotating slowing down. So let's understand angular velocity using this clock. This clock has a hand. So this hand will rotate one complete circle in an hour. So what will be the angular speed of this hand of minute? So in 1 hour, it will have an angular displacement of 2 pi, which is one circle, over 1 hour, which is, and the unit should be reading per second. That's the angular speed of the hand of minute. And then how about angular acceleration? Now if you look, the speed of the hand of minute doesn't change. So if change of angular speed is 0, your angular acceleration must be 0. We have learned the 5 kinematic equation of constant acceleration. We have found out that there is also a one-to-one correspondence between linear motion and angular motion. You have displacement corresponding to angular displacement, velocity corresponding to angular velocity, acceleration corresponding to angular acceleration. So which means if you do this replacement for all the variables, you get exactly the same 5 kinematic equations. Which means if you are good at applying those 5 kinematic equations to find unknown variables, you should be good using those 5 kinematic equations to find unknown variables as well. And now after we learned kinematic equations, eventually maybe we are interested in linear motion of this rotational motions, and how do we relate angular kinematic variables to linear motion variables. And there are also simple relations. For example, you have one object doing uniform circular motion along this circle. So, of course, if you rotate one circle, the distance it traveled must be 2 pi r, right? The circumference. So if you just rotate a quarter of this circle, then the angle is a right angle, which is pi over 2 or 90 degrees. So the distance you traveled is pi r over 2. So this angle is pi over 2. So which means the linear displacement is always just angular displacement times r. And then we have used this to prove. We have learned this in uniform circular motion in chapter 6, uniform circular motion and gravity. We have acceleration. The centripetal acceleration is r omega squared. It also equals to v squared over r. Now you can see there is a relation between velocity and angular velocity. See, your velocity is just r times velocity, and then your acceleration, actually, this is your, now, make sure you understand acceleration is a little bit trickier than this. So basically right now we have displacement equals angular displacement times r, velocity equals r times omega, but this is AC equals r omega squared equals v squared over r, which is not the acceleration we're used to. Actually, we also have, let's call it tangential acceleration or translational acceleration. That it equals to r times alpha. Alpha is angular acceleration we're talking about. Now, let's talk a little bit more about AT and AC so you don't get confused. AC is this one is always pointing to the center of this uniform circular motion. Now, uniform circular motion is angular velocity is a constant. It doesn't change. But however, if the motion is not uniform constant motion, omega can change, and you are going to have an alpha. So let's draw it somewhere else. So if we are doing a circular motion and its angular speed is not uniform at all, you might have an AT, and then AT depends on how your angular acceleration is, r times alpha. But anyway, for any circular motion, you always have AC equals r omega squared equals v squared over r. For AT, if you have an angular acceleration, then you have AT. If you don't have angular acceleration, you don't have AT.